Welcome to Basic Mathematical Analysis class. Today we will discuss about contractive sequences. Last class too we have discussed the definition of contractive sequences and some of its properties. And a theorem we have also studied one theorem. And contractive sequences by definition, we say that a sequence x equal to xn of real number is contractive if there exists a constant c such that c value is lying between 0 and 1 and modulus of xn plus 2 minus xn plus 1 is less than or equal to c into modulus of xn plus 1 minus xn. And we have studied a theorem, every contractive sequence is a Cauchy sequence and therefore it is convergent. So first of all, every contractive sequence is a Cauchy sequence and therefore it is convergent. And we will have this idea, that is whenever you are finding xm minus xn, you will get this as c raised to n minus 1 into 1 by 1 minus c into modulus of x2 minus x1. This thing we will make use in proving a corollary today. And we have seen one example. That example resulted golden ratio. So today we will start with the corollary. If x equal to xn is a contractive sequence, so given that our xn is a contractive sequence with a constant c and the value of c lying between 0 and 1, then x star, when you're finding x star to be the limit of x, then modulus of x star minus xn is less than or equal to c raised to n minus 1 by 1 minus c into modulus of x2 minus x1. So this is the first thing. So we will prove this. From the preceding proof, if m greater than n, we have got this quality, that is modulus of xm minus xn. This value is less than or equal to c raised to n minus 1 by c raised to n minus 1 by 1 minus c into modulus of x2 minus x1. Okay. Now, suppose m tends to infinity. What will happen? M tends to infinity. This will reduce as x star. So, x star minus xn. This side, no xm term. So, this is less than or equal to, you will get c raised to n minus 1 by 1 minus c into modulus of x2 minus x1. So, we have got that one, right? For this, we have made use our previous proof idea, that is we are dealing with for proving it to be a Cauchy sequence. We have made use this idea. See, this one only we have used here. This one. See, this idea we have used. And now we have got the first corollary. Now we will pass to the second corollary. Second corollary says that whenever x star is again going to be the limit of the sequence. So whenever the limit of that sequence x star minus xn is less than or equal to c by 1 minus c into modulus of xn minus xn plus n minus 1. So we can see how we can prove this one. So to prove, recall if m greater than n, we have got this like this. Xm minus xn is less than or equal to modulus of xn minus, this we have seen by writing xn minus x xm minus xn whenever m greater than n. We can write this as xm minus xm minus 1 plus xm minus 1 minus xm minus 2 plus etc. Last time should be xn plus 1 minus xn. Now use the triangle inequality, right? So like this. Now you can use the triangle inequality. Therefore, modulus of xm minus xn should be less than or equal to modulus of xm minus xm minus 1 plus modulus of xm minus 1 minus xm minus 2 plus etc. modulus of xn plus 1 minus xn. We have already seen this using triangle inequality. Since it is readily established using induction that xn plus k minus xn plus k minus 1, this value is less than or equal to c raised to k into, these two we have seen, right? C raised to k into modulus of xn minus xn minus 1. From where you got this one? We will use induction steps to show this. See, from here itself we will get xm minus xn. So, here is coming c raised to n minus 1 term, right? So, when you are finding previous results and domains, see this one, this star marked one, this only we are making use of. We used the induction method to prove like this. So, instead of xn plus 1 minus xn plus 1 is coming means you are getting c raised to n plus 1, 2 minus 2, right, into x2 minus x1. So we will use that here. Yeah, this one. Now we will get this equal to xn plus k. So xn plus k minus x n plus k minus 1. This is less than or equal to c raised to k into modulus of xn minus xn minus 1. And we will get modulus of xn minus xn, which is less than or equal to c raised to m minus 1 plus etc. c square plus c into modulus of xn minus xn minus 1. And this value is less than or equal to c by 1 minus c into modulus of xn minus xn minus 1. Since this will form a geometric progression, right? Geometric progression is like this: c raised to m minus n. Next term, c raised to m minus n minus 1, right? So, etc. Last term should be c square into c. So, this is a geometric progression, right? With common ratio 1 by c. Common ratio is 1 by c. Now, we know the sum of n terms of a geometric progression too. Okay, and that value is, we can replace this with an infinite geometric progression, right? So when you are replacing that, its sum is going to be c by 1 minus c. Okay, so this entire value is less than or equal to c by 1 minus c into modulus of xn minus xn minus 1. Now what we have to do? Let m tends to infinity. So when let m tends to infinity, what you are getting is modulus of x star minus xn. This value is less than or equal to c by 1 minus c into modulus of xn minus xn minus 1. So this was the corollary 2. So we have proved the corollary 2 also. Corollary 2 was x star minus xm is less than or equal to c by 1 minus c into modulus of xn minus xn minus 1. Next we are having an example. The cubic equation. Consider the cubic equation x cube minus 7x plus 2 equal to 0. Now this has a solution between 0 and 1. It's given. Okay, given it has a solution between 0 and 1. Now we want to find the solution. We know only the fact that the solution lies between 0 and 1. Now this can be done by means of iteration procedure. Iteration procedure means you may study it under numerical analysis class, but it's iteration process. So first of all, we will have an approximation to this value and we will go on improvising that value. Then we will say that such a method is an iteration procedure. And in numerical analysis case, when you are getting in each step improvised values, and we will stop that improvisation if you are getting two values very close. This can be accomplished by means of an iteration procedure as follows. So first we rewrite the equation. So we will write this as x equal to x cube plus 2 by 7. So when you are reducing, it will become the same equation, right? So first we have wrote it like this and use this to define a sequence. First of all, we will define using this, we will define the nth term. So the nth term of the sequence is xn plus 1 equal to 1 by 7 into xn cube plus 2 for n belongs to n. Right? So for the first term should be, suppose you are putting n equal to 1, you will get x2 equal to x1 plus 2 by 7, like that. Now what you follow is, since 0 less than x1 less than 1 is given, it follows that all the xn value also lies between 0 and 1. Since x1 value, it's given that x1 value is less than 1. So when you are finding x2, so n equal to 2, that is 1 by 7 into xn cube plus 2. Sorry, x1 cube plus 2. x1 value is lie between 0 and 1. So what about x1 cube value? That will also, because see, this is 0 and this is 1. So I will take a value 1 by 4 here. Value lying between 0 and 4. So when you're finding is cube, I will get 1 by 4 cube. So that should be 1 by 64. Again less than 1 by 4 I am getting, right? So this value again should be less than 1. And this value should be always greater than 0 also. So like this, all our xn values will lie between 0 and 1. Now we have modulus of xn plus 2 minus xn plus 1. That's equal to, just you substitute the values. Right? Xn plus 1 means, sorry, xn plus 2 means 1 by 7 into xn plus 1 cube plus 2 minus xn plus 1. Using this xn term idea, you will substitute that, it will get 1 by 7 into xn cube plus 2. Now this will reduce as 1 by 4 into xn plus 1 cube minus xn cube, because plus 2 and this minus 2 will get cancelled. So remaining value should be this. Now this can be written as 1 by 7 into modulus of xn plus 1 square plus xn plus 1 into xn plus xn square into xn plus 1 minus xn. When you multiplying this, will you get this? See, xn plus 1 into xn plus 1 square, you will get xn plus 1 cube. Next value, xn plus 1 into xn, right? The same way, you will get xn into xn plus 1 value also, right? So this is minus value, this is plus value, it will get cancelled. So the next term should be xn square minus xn. So it will result xn plus 1 cube minus xn cube. The same way you will get. Now this value is less than or equal to, see here, you will get this value. You have already know this is less than, value is less than 1, right? So you can replace that here. So get this value as 3 by 7 into modulus of xn plus 1 minus xn. Therefore, what you are getting is, you got this value is less than or equal to some c into this. Now, what about the c value? Will it be less than 1? Greater than 0? So, since 0 less than 3 by 7 less than 1, this will result a contractive sequence, right? Now, this contractive sequence means it's a Cauchy sequence. We have proved that. Now, this will converge us, right? So, therefore, our xn is a contractive sequence, and hence there exists in R such that limit of xn equal to R. Now, we want to find what is this R value. Okay. Now we'll pass the limit on both sides of the inequality. We will get xn cube plus 2 by 7. We obtain r equal to r cube plus 2 by 7. That means r cube, you can have the equation r cube minus 7r plus 2 equal to 0. What is it? A quadratic equation, right? So we can approximate r by choosing x1 and calculating x1, x2, x3, etc. Right? So if we take x1 equal to 0.5, 0.5, if you are taking this, you can put your own value in between 0 and 1. Then you will get, see, x2, some value you will get, x3 another value, x4 another value, x5 and x6. See here, when you are writing x5 and x6, what is the difference? Up to 6, up to here the same, right? Now 0.0000001 something is coming, right? So the difference is very less. So at such a stage, we will stop the procedure. Now to estimate the accuracy, we note that x2 minus x1 is less than or equal to or less than 0.2. Thus, after n steps, it follows from the corollary that we are sure that x star minus xn is less than or equal to 3 raised to n minus 1 into 7 raised to n minus 2 into 2. Thus, when n equal to 6, we are sure that this value, see, it follows from just before we have seen that this is 2 by 3 into something is coming now, one value, sorry, 3 by 7 into something. See, I'm telling about this value, see this value. So like that, if you are giving some or assuming some value for x1, you can go on finding x2, x3, x4, and its value or the difference will lie between 3 by 7 into modulus of xn plus 1 minus xn. So in x6 we have taken, I have said no, the difference is very less. So it's coming up to this. So we will say that X is going to be a solution. Next definition is properly divergent sequences. Definition: let Xn be a sequence of real numbers. We say that Xn tends to plus infinity or minus infinity and write limit of Xn equal to plus infinity if for every alpha belongs to R there exists a natural number k alpha such that if n greater or equal to k alpha, then Xn is greater than alpha. For example, suppose you have got the sequence n. Sequence is going to be n. So Xn equal to n. That means the value is 1, 2, 3, 4, 5, 6, 7, etc. It's going like this. Now Xn tends to plus infinity. This we know. For that, you take an alpha belongs to R. You take the real number 0, 0, 0, 0, 0, right? Then there exists a natural number k of alpha such that after a certain stage, this n value is greater than our this k of alpha value. So it is k of alpha. Then definitely you can find in this after what's the stage 1, 0, 0, 0, 0, 1th stage onwards. If this is the stage here coming here, now this stage onwards, every element should be, if there is an x, means this x should be greater than this value, right? 1 lakh. So this x should be greater than 1 lakh. So if such a case is existing, means we will say that this sequence tends to infinity, plus infinity. So limit of Xn, we will say that this is plus infinity. Now there is we say that Xn tends to minus infinity, and we will write limit of Xn equal to minus infinity if for every beta belongs to R there exists a natural number k of beta such that if n greater than k beta, then Xn is less than beta. Here we have seen that Xn is greater than alpha. But when you are saying that it converges or it tends to minus infinity, means your xn value should be less than beta. Now we say that xn is properly divergent in case we have either limit xn tends to infinity or limit xn tends to minus infinity. I think you're clear with this definition. So with this definition, I'm winding up today's session here. Thank you for your patient listening. Thank you.